On the other hand, we've got a lot of good things to talk about tonight, and for those of you, just to make sure you're in the right place, this is the first of 4 campus conversations regarding kind of the future of what we're going to be doing with the central heating plant and Carleton's, excuse me, wrong college, sorry, and Oberlin's plan for moving to a fossil-free, carbon-neutral type of environment by 2025, which is the goal that we have. So again, thank you everybody. My name is Rob Lamppa, and I'm the Director of Sustainability and Energy Management at Oberlin College, and have been here for just a little over a year and a half, and have been asked to work with the staff and the faculty to come up with a plan for the next generation of heating and cooling across the campus, aimed to provide a number of things, kind of an update to the dated technology and infrastructure that we have to provide us with a reliable source of energy, as well as to work toward a clean and renewable future. Also with me tonight and in the audience, and will certainly be a part of our questions and answers at the end, are Professor David Orr and Professor Emeritus David Benzing, both who will provide a historical perspective with regard to maybe some of the other alternatives that have been looked at in the past, and provide comments as to where we're going. So this plan has been put together with a consortium of people, and we've had a number of reviews and meetings and such to provide updates all through last year with the consultants that we've used. But we'll talk about that a little bit more as we get moving forward. At this point, this is pretty much what I want to go through, give a little bit of background for kind of where we've been, talk about the existing system, where we're going with the energy footprints and some projections, what kind of resources for energy are actually available here in Oberlin. Obviously, there's things that are happening all over the country, but not every place across the country has the same resources available to it. So some things that might work in the Southwest might not work here. Things that might work here might not work somewhere else. So we'll talk a little bit about what do we really have available for us. Talk a little bit about what some other schools have been doing, kind of in an overview. There will be another session, probably the 3rd session, we'll have more related specifically to stories from other campuses on the kinds of how they've tried to address the same challenge. And then what options we've looked at, looking at a centralized versus a regional approach, and then where do we go from here. So again, Oberlin College has been a leader in sustainability, and certainly has been doing that. There's a long tradition of that here. It's ingrained into a lot of the things that we say: comprehensive environmental policy, a strategic plan, the fact that we are issuing STARS, which is Sustainability Tracking Assessment Rating System, and we have worked with the American College and University President's Climate Commitment to develop a carbon neutrality goal of 2025. It's also reflected not only in things that we say, but the things that we've actually done on campus. We have 5 LEED certified buildings. 2 are gold rated, which are brand new buildings. We have a gold rated renovation. The Con Residence Hall was LEED silver rating, and the Apollo Theater, which has just newly been renovated over the last summer, and with a lot of extra hard work with Leo Evans, who's also in the audience here, has come in with a LEED certification. The Lewis Center, the building that we're in here, certainly was named the most important green building constructed in the last 30 years by the AIA Architect magazine. So Oberlin has been ahead of the pack. We've been leading the way. We've been pretty much a standard for schools across the country. So again, our policy statement here. The policy statement was adopted by the board in March of 2004. But basically what it is, we have to make sure that we educate students. We have to demonstrate by our actions that we are responsible stewards of our environment. And then we need to certainly increase the rate of renewables and reduce the rate of depletion of natural resources. This policy right now is under review by the Committee on Environmental Sustainability. We're trying to take a look and upgrade this to 2012. As you can see, it was done in 2004, so we're trying to update it from the last 8 years. It is also a key component of the Oberlin strategic plan. And again, it's much the same as in the policy. Again, reduce the rate at which we consume resources, increase renewables, implement state-of-the-art standards, as this building has been and certainly is, and ensure student and faculty involvement and education are a big piece of that. American College and University President's climate commitment is something that, as you can see, just under 700 schools have signed across the country to try to take a pledge to work together to try to bring the concepts of sustainability, energy efficiency, and awareness and responsible living to students, to the next generation, so that these students, as they live and work on campus, will be able to take those habits, those ideas, and move out into the new jobs that they have and the new professions, and try to make sure that this spreads across the country. I mean, we have a responsibility as educators of the next generation of leaders and entrepreneurs to do this type of thing, and Oberlin stepped forward and was one of the first to do this. As you can see, there are many other institutions in our geographical area, as well as a number of them for the same type of private four-year liberal arts colleges that have all signed on. So what does this mean? We have to do a number of things for this. The commitment that the college made with regard to the Climate Action Plan said that we needed to create a committee to see that we move forward with the items on the climate commitment, which was the Committee for Environmental Sustainability. We had to commit to set a date or set a goal for carbon neutrality, which we have done, which is 2025. And then we have to develop a plan aimed at reaching that goal, which is currently underway. We did have an initial plan which was posted on the ASU website in 2010, but since then some of the technologies that are available to us here in Oberlin have changed, and therefore we're revising the plan, and part of that will be outlined in this presentation. Central heating plant certainly is a big piece of that, and I'll talk a little bit about what our central heating plant is. And many of you ever been through the plant? Obviously, one person in the back certainly has, and a few of the rest of you. If you've ever had a chance to get through any of the central facilities on any campus, it's always extremely interesting. We have the two coal-fired boilers, which are solid fuel boilers on the east side of the building, and one natural gas boiler, which is on the west side of the building. The maximum steam required on average for heating the campus is approximately 65 to 70,000 pounds per hour. And with regard to this, we have 375 kilowatt co-generator. What that means is that these boilers, let me back up a second. The co-generator means that we use some of the energy from burning of the fuel to create steam, which spins an electric turbine, which creates electricity. When we get the coal boilers on in the middle of the winter, the steam that comes from those is used to drive the co-generator. So we do produce some electricity in the wintertime, which then we don't have to purchase from the local utility. I'll talk a little bit more about some of that in a second. The building, east side especially, is roughly late 1940s construction. It's starting to get to be toward the end of its useful life. We are having limited availability of some of the parts for maintenance and repairs, and so it's getting to the point where we probably need to do something. I mean, the boilers have certainly met their useful life. They've been very dependable and they've been utilized, and the crew who operates the facility has certainly stretched them long beyond what people thought they were going to last. We have air emission regulations which are pending in 2015, which will require additional emissions control, and we'll talk about that a little bit. And also the campus has a desire to reduce its carbon footprint. In other words, moving away from fossil fuels to fuels that are carbon neutral. So there is a change that's required. Now, the central heating plant is only operated during the heating season, unlike many central heating plants at other colleges and universities across the country. The natural gas boiler, which is a little bit larger than each of the coal-fired boilers, is operated on what we call the shoulder seasons. In other words, as the temperature fluctuates up and down. Some days it's hot, some days it's cold, some days it's not. The natural gas boiler is a little more flexibility, and so we operate that until we get to the certain point where we have a base heating demand, and then the coal-fired boilers are fired up. First one is, and then the second one is, and they run through the bulk or the heart of the winter. And then as we come back into spring again, the natural gas boiler is fired up, and then when we don't need heat anymore, all of them are shut down. The central heating plant isn't operated at any other time except during the heating season, and that's roughly between 5 and 6 months at the most. Last winter wasn't that long. So for the centralized system, all the buildings in pink are pretty much the ones that are served by the central heating plant. Building number 39, which is right at toward the left center of the page, is where the central heating plant is, and we have over 7 miles of underground steam lines which bring steam to all the buildings. Some of it is circulated directly through the buildings for heat. Others, it goes to a heat exchanger and is converted to hot water, which is then distributed through the buildings for heat. But it's one spot feeds all of these different buildings, and the Oberlin Inn, which is not shown in pink, which should have been.
And First Church.
And First Church, absolutely. And I believe also, David, didn't we used to serve the hospital as well at one time? And I think they have their own system at this point. So anyway, greenhouse gas inventory for fiscal year 11 shows that we were at roughly 45, almost 46,000 metric tons of carbon dioxide. The total at the end, which we report to the College and University President's Climate Commitment of 40,000, has been offset because we bought roughly 6.4 million kilowatt hours of renewable energy credits. And as you can see, purchased electricity 46%, the coal and natural gas that we burned is another 47% there. So those are the 2 largest portions of where we create our carbon footprint. Fiscal year 12 was a little bit better, but that was mainly because if you take a look back, you can see the coal burned in fiscal year 11 was roughly 7,000 tons. And if you take a look at fiscal year 12, which was last winter, as you can see, it was only 4,600. So that tells you how much warmer a winter we had, and that was one of the main reasons for the reduced amount of carbon. But still, again, it made the electricity up to 50%, and again, 40%, 42% for the heat. Kind of I put 2007 in this slide because that's kind of our baseline year as per the College and University President's Climate Commitment, and give both the reported carbon as well as what our energy intensity is. And energy intensity really is a better, well, you kind of have to look at both combined. The energy intensity, since all of our fuel is mainly fossil fuel, does give us an indication of the kind of efficiency we have on campus. However, there are other colleges, such as Middlebury, for example, and I'll talk a little bit about them. They have a lower carbon footprint than Oberlin does, but their energy intensity is over 200,000 BTUs per square foot per year. So even though you might say that the biomass boilers they have are carbon neutral, they aren't really educating their campus to reduce energy. And both of those really have to go hand in hand to make any real reductions, because the thing is, we can't continue to send people out into the world utilizing the same levels of energy. So Oberlin is definitely making progress, as you can see here. As you can see in fiscal 12, our energy intensity again was down to 122,000. Here are some other energy footprints from other similar colleges. I had worked at Carleton College before, so the blue bar is Carleton. It's just under 120,000 BTUs per square foot per year. As you can see, most of the rest of them are at that point or a little bit less. There's a couple that are higher. Our average is probably closer to 130,000. 75% of that's from heating, 25% from electricity, but we really could be much less than that. So we can do some work on efficiency and how we utilize the energy that we have. So what do we have? Well, obviously we have coal, and that has been an issue, and I think historically has been an issue that the colleges wanted to change for years. It has been the least expensive fuel available, but costs are rising. And if we have any type of carbon legislation coming forward, those costs would rise even more dramatically. Greenhouse gas emissions obviously are the worst, and we also have sulfur dioxide, nitrous oxides, particulates, and mercury emissions, which are currently going to be under greater control requirements by the regulations than they currently are, so the college would have to invest significant money into the existing plant if we were going to continue to operate it the way we have. But this is solid fuel. It's trucked in from southern Ohio, so there's some carbon footprint with that. And we have a lot of storage and handling. And the other thing that a lot of people don't think about is the ash is the college's responsibility, no matter where it goes, because if something happens and ash has an either toxic effect or ends up somewhere it hadn't been, the EPA goes back and takes a look at everybody who contributed to that. And everybody then will have an opportunity to participate in the cleanup. So again, ash, like many other types of solid waste or any waste that the college generates, it's ours from cradle to grave. We also have natural gas, and certainly that has been something that has been somewhat controversial in the way it's been developed in the last decade or so. And we will be having additional conversations to talk about those issues specifically. If you take a look at just the combustion portion of it, it does have 44% less greenhouse gas emissions when combusted than coal does. However, it's roughly twice as expensive as coal on an energy basis, but those costs are going down. So as we're looking at things, coal prices are rising, natural gas prices are coming down. But at this time, we estimate that even if we replace on a BTU per BTU basis, which means a heat value to heat value, the college would probably incur somewhere between $500,000 and $1 million more per year operating cost, even just to convert to natural gas. There is a ready supply, and it doesn't need to be stored. And part of the flexibility of it is that it can be turned on and off. Let's talk a little bit about biomass. We've looked through a lot of the literature, and probably the greatest percentage of what's available in this area is agricultural residue, mainly corn stover and bean stover. Basically what that means is all the residue left after they picked all the corn and thrown all the rest of it in the fields. That certainly would take a lot of energy and effort to try to pull together and to wrap up and haul somewhere. The density of this type of fuel is much less than coal. Coal is a very dense material, not only physically but also in its BTU capacity. So if you take a look at both the BTU density as well as the actual physical density, we would probably need, on a volume basis, 10 to 14 times the volume of fuel that we do with coal at this time. So staging and maneuvering it and getting it and storing it ends up being a large place. And currently we don't have any space around the existing central heating plant to look at this. The other thing about it is that there's more studies coming out that show that from a combustion standpoint, it puts out very close to coal as far as the greenhouse gas emissions. Now, the thing about it is that we have to take a look and say, how quickly can this product be regrown? The only way it would be neutral is that if you use current carbon and you burn it, and then you grow just as much as what you burn to pull the carbon back into the plants, then it's technically neutral. But if you start burning trees and they take 40 and 50 years, that means you won't sequester that amount of carbon for another 40 or 50 years. So it really depends on which type of fuel and what it looks like. But again, as we're looking at it, you have to consider how much and where it goes, and then also where are you going to be getting it from? How is it going to be shipped? How is it going to be managed? Is it going to be from sustainably managed forests? Is it going to be from sustainably managed farm fields or wherever it would be grown, and at what cost per ton? At this point, we don't have a readily supply of woody biomass close to here. We could maybe truck enough pellets from northern Michigan or North Carolina, but again, we start running into the transportation charges, and then you have to say, how carbon intensive is it? The other thing is, if you remember, I talked about the fact that we only run the central heating plant roughly half a year at the most. Could we get a half a year's supply? Most of these places would like you to have a full year's supply in order to be able to sell you. And then again, let's say you're using something like switchgrass, which is an annual or maybe grows in 3 years. What happens if you have a drought year? Where are you going to go to get the biomass from? Again, staging and distribution we talked about, and the fact that we don't have a redwood supply available means that we probably would need to have some type of backup system. And I'll talk in a little bit, but even the other studies we have where the recommendations came out that a biomass facility might be feasible, both recommend that you would have a natural gas boiler system as a backup. So again, we talked a little bit about how much carbon neutral, and if we look down at the bottom here again, if truly, which was being pushed at one time by Bill McKibben and others saying we would like to get to 350 by 2050, if everybody converted from natural gas or coal to biomass right now, we would actually be putting double the amount of carbon into the atmosphere over the next 50 years than if we were just converting natural gas itself. So part of it depends on what does that mean. I know Professor Orr's talked about the fact that storms like Hurricane Sandy are the result of what we have done 25 to 30 years ago. What will be the ramifications as we move forward if we can't control this by 2050? The other thing that we had hoped would be available here, and what the previous climate action plan had been based on, was landfill gas. As you're aware, the Lorain County landfill is only 2.5 miles away. It produces a fair amount of gas, and it seemed like might there be an opportunity at some time to be able to procure that gas, to have it cleaned up and piped to the college for use. Well, at this point, one thing we have to remember too is it's also only has half the heating value of natural gas. And the college doesn't control us, and the Lorain County landfill doesn't. There's a company called EDI, which is an Australian company, owns the right to the landfill gas production. What they're using it for, as you can see the photo on the bottom, is to burn in generators to make electricity to send to the grid. So we have tried to talk to them because at one point they said within the next 5 years there might be some available. The amount that they had available wouldn't have been able to meet all of the college's needs, but we would have been maybe able to use it for a portion of the campus. Now they have stated, since the earlier cells where they had first begun their electricity production are starting to wane, they want to take the landfill gas from this latest cells and pipe it to the first one so that they can continue to run their generators to make electricity. They've just gone through a major expansion at the landfill and have added 10 megawatt production worth of, actually it's closer to 16 because I think they had 8 and then they were going to add another 16. So they've got a very high amount of electric production over at the landfill at this time. The other thing we had hoped is could we recover the waste heat from them running the generators? Could we put a heat recovery unit on that to heat up water and then pipe it to the campus for reuse? Well, the 2.5 miles with the volume of hot water that we would need to heat the campus gets to be the point where we couldn't build a large enough pipe or afford to bring it the 2.5 miles here and then to send the return hot water back to be reheated again. So at this point, it hasn't been cost effective. And because landfill gas, sometimes cleaning it up gets to be a little bit tricky depending on which cell it comes from and what the concentrations of the different types of wastes that are in that cell of the landfill are, you get a little different composition. And then it means altering the treatment for it because it has siloxanes, it has mercury, it has a number of things in it that you have to take out before you can burn it. So therefore, while that's happening, you would still need to have a natural gas backup system. Biogas, again, methane produced. We certainly have some food waste here. The community has food waste and other compostable waste. There might be a possibility that we could develop an anaerobic digester similar to the city's sludge digester at the wastewater treatment plant. But it looks at this point that under ideal conditions, the college would need between 50 and 75,000 tons of organic waste per heating season just to create the base load for the campus. There is also, we would have competition in the fact that there's a large facility coming online in North Ridgeville by the Quasar Company, and they have been scouring Lorain County for enough to fill that unit. In fact, they've already been down to the college, they've been across the campus, they've been to the nurseries trying to find out what level of biomass might be available that they could use to bring to their digester to continue to make biogas. So it is unlikely that there would be enough organic product on a consistent basis at this time to fuel the whole campus. And even with that, again, you would want to have natural gas as a backup in the event that you ran out of material weren't able to get it, or there was an issue with it. Here's a biogas plant that I was at in Norway in 2008. You can see the large digester on the right side of the picture and the white sphere for gas storage. The trucks bring in all the waste. It goes through the rotating drum to get rid of all the plastic bags. And then they run it through this stainless steel cooker to first sterilize all of it, and then they run the remains into the digester tanks and start creating the gas. And then they use the gas to run the generators, which are on the lower right picture, to create electricity. So, we talked about gas and coal and fossil fuel and such. What are our solar and wind resources here? Wind speeds at 50 meters, and I have maps for both 50 meters and 80 meters. This one was, the 50 meter one was a little bit clearer, and I think it shows here that if you take a look at the delineation between brown and white, and you look down in the chart at the bottom, brown and white are the two lowest wind speeds that are available on the map. Now, if you look where Lorain County is on there, you can see that we're right at the border between the brown and the white. 50 meters and at 80 meters. This area is just below the threshold of where it becomes economically viable to build a large-scale wind turbine like the one you saw in the previous picture. So at this point, we haven't pursued that. Should the technology become better to where we could leverage that in the future, we would take a look. As you can see up by Lake Erie, and some of you may have seen large wind turbines up in the Cleveland area, there is quite a bit of wind resource up by the lake, and that's why those wind turbines are there. Here's a map of the solar insolence that hits the country. And if you take a look at where Ohio is and Lorain County, we're right on the border between the light brown and the next shade of brown. And again, if you look down on the scale, the browns are kind of in the not so good range, and the oranges and reds, which are down in the southwest part of the country, are the highest. So the area where we're located here in northeastern Ohio, western New York, and northwestern Pennsylvania are not the best area for solar. However, we were able to put a project together here, certainly in Oberlin. If any of you have been up by the north and west of the athletic field and seen the new system, it was just commissioned last week. It is fully online and producing electricity. And we should be getting some data for that for those that are interested in it in the next couple of weeks or so. And all of these are on a single axis tracker, and the panels track the sun during the day. There's a couple of other pictures. You can see how they're flat in the middle of the day, pointing straight up, because these rows are in a north-south direction, so they tilt from east to west. And then you can see on the right-hand picture where all the panels are all lined up in the rows, pointing toward the east. We do have GeoExchange here, and we have several buildings around it. And GeoExchange is another name for ground source heat pumps or geothermal. You could go for one building or groups of buildings to do that. Ground source heat pumps, like I said, is another one. We have 3 buildings. This building was the first one to go on GeoExchange system, and it basically is responsible for all of the heating and cooling for this building. There is an electric boiler backup. The Coal Jazz building is also a complete building, and I don't believe there even is any backup for that system. So they're in the process of tweaking that because there's still a few things to go with it. And then the Memorial Art Museum, I believe, Leo, is a hybrid system. Is that correct?
Yeah.
And so what that means is that we've got a geothermal or GeoExchange system that will take care of the bulk of the heating and cooling, but we will have more conventional means which will supplement the GeoExchange on the coldest days and on the hottest days. It is one of the few really renewable resources available, and it is one that we have tried to work into our plan as to how we're moving forward from here because it has some cost-effective viability. Again, it works most effectively on year-round buildings that are both heated and cooled, or if you can put a group of buildings together, like we'll talk about a little bit in the regional scenarios, where buildings could be heated in one group of buildings could be heated in the winter, and you could take the cooling load from another building to offset the heating load for the GeoExchange well system in the summertime, and then maybe heat it with conventional means. But again, it would be an all-electric solution, and we'll talk about why that would be a good thing here in a minute. Again, geo-exchange systems have a good coefficient of performance. Most of they are run between the 2 to 4 range. 3 to 4 is common, which means that for every BTU of energy that's put in, which circulates the fluid through the geo-exchange system and transfers the heat, we actually get 3 out, because in the summertime, or in the wintertime, we're pulling heat out of the ground, and in the summertime, we're putting heat back into the ground and cooling off the buildings. And in doing that, it's much more efficient than using just a regular radiant electric heat, which would only have a coefficient of performance of 1. So this is 3 times more efficient than that. So again, if we can consider a 3.5 times, it means that it's very close to being on par with the cost of natural gas. Again, one thing that is similar technology but doesn't use a well field to exchange temperature are air-to-air heat pumps, or variable refrigerant flow systems. Again, you want to use them. They can be heated and cooled. Many of you may be familiar with one side of that, because these types of heat pumps are very similar to a central air conditioner that you may have in your own homes. If you go out and take a look at that unit that's sitting outside by your house, and it has a fan going and you can feel all the heat coming out, that is because they're dumping the heat out of your house and putting it outside. Now, if you ran it in the opposite direction, where the cool was on the outside in the wintertime, you could pump all the heat back into the house. So we could use these types of things on some of our smaller buildings, or on our buildings that didn't have as large a demand, so that we would, again, continue to minimize the amount of conventional technology. It wouldn't be able to, again, cover the extremes, but we would be able to pick up most of this. And for every hour that you could run an air-to-air heat pump, means that we would be saving that much on fossil fuel. So why move to electricity? I mean, is it electricity from coal-fired power plants or natural gas-fired power plants? And if you took a look at our earlier greenhouse gas emissions, I showed that 50% of the greenhouse gas emissions came from electricity. So why would that be better to move to electricity than staying with conventional fuels? Well, it's because the city, municipality, and through their power, through their utility, Oberlin Municipal Light Power System, will be providing renewable energy to the community by 2015. They have invested in long-term contracts with landfill gas, with 2 different landfills for landfill gas, and in a large hydro facility on the Ohio River. So therefore, all the electricity that they purchase from those areas, they will keep the renewable energy credits, so it will be green. And by reflection, then, all of the electricity that the college uses will be 90% carbon-free. Therefore, if we can take advantage of that by moving our heating and cooling to electric means as opposed to fossil fuel, then we will have that be from 90% renewable resources. Here's kind of an overview of what some of the others are doing, because there is some information out there that somebody else has it all figured out. Why doesn't nobody just look at what they're doing and have it all figured out too? So I started to take a little bit closer look into some of these, and Ball State is one, because they are doing a massive $85 million project to do district geothermal for a good portion of their campus. This district geothermal system will replace the 4 coal-fired boilers that they have on their campus. However, they do have 3 natural gas boilers, which will be used to supplement this system on the coldest days. And then they will also run their chilled water system on the warmest days to be able to hit the peak demands for cooling. They've gone so far as to put sensors into their well field so they can actually measure the temperature of the soil within their well field. And if they have to, they will heat the fluid that goes back into the ground in the event that the ground is getting too cool, or they will run a cooling tower on one end of it and send cool fluid back through it to cool it down if it's becoming too warm. So they're going to be operating a hybrid system. It'd be extremely interesting to watch how they proceed, because this certainly will have a huge impact on what they're doing and on their carbon footprint. University of Central Missouri is doing something similar. They're developing a district hybrid system for part of their campus as well. Middlebury College, who I referred to earlier, does provide a great portion of their heating with a centralized biomass boiler. and they have gotten a lot of recognition for that, and rightly so. They're one of the first colleges to move to biomass. They're sitting right in the Green Mountains of Vermont, and they have a lot of biomass and wood products available to bring there. In fact, they're even developing some areas on their own property to grow willows to try to see if they can cut and to feed their biomass boilers. However, even as good as this is, they still burn 1 million gallons, number 2 and number 6 per year, and that's fuel oil. And if you take that conversion, it's just about it's the equivalent of 5,000 tons of coal. And if you think back to the fiscal year 12 greenhouse gas inventory I showed you, that winter we only burned 4,800 tons of coal on this campus. So not only are they operating, now they're in a little bit colder climate than we are, so we'll give them some of that, but it comes back to that energy footprint I was telling you about as well. Not only are they burning their biomass, but they're also then burning this 5,000 ton equivalent of fuel oil as well. University of Minnesota at Morris, they are taking agricultural waste, corn stover from the areas, and they have a biomass gasification system. They had an extremely aggressive carbon neutrality date of 2010 they were trying to meet. They pushed it back to 2012, and when I just talked to one of their people, they were thinking it might have to go back to 2014 because they've been having trouble with the gasification system. Now, it doesn't mean that they don't want to do it, it doesn't mean that they can't do it. This is a research project for them. They're trying to see how well this works and have themselves be a model for this type of thing across the country. But they've been running into a lot more silicates in the corn stover and other agricultural residue, which is glassifying. They're gasifying the gas and they're burning that gas, but there's still enough silicates in it that it's glassifying the tubes on their heat exchangers, preventing the appropriate exchange so they don't get enough steam through their boilers. So they are still trying to work through that system. Green Mountain College, again, another large wood chip biomass boiler, and they're just a little bit south of Middlebury, and they have, they're planning to eventually get up to 80% of their heating load, but they are still planning to burn the 20% of more conventional fuels, which is fuel oil. And unfortunately, in that part of New England, there isn't a lot of natural gas because they've got so many mountains that can't get it through there without cutting a lot of trenches in the rock. And so therefore, they have to haul fuel oil to do that. Now, the University of New Hampshire is using landfill gas. They're one of the first universities in the country to convert some of their major boilers to landfill gas. They have a very large landfill, but for what they're going to use, they're figuring they only have it for 20 years. They don't know if there will be any more available after that. So they have natural gas as a backup for that boiler if it isn't supplying, and it also provides the rest of their demand. Now they're going to try to slowly see what else they can do, but their carbon neutrality date is 2099. Denison, just south of here, is in the process of master planning, and they're looking at replacing their coal-fired boilers with natural gas. And Worcester is also planning to do the same thing. Again, here are some of the climate neutrality dates for these institutions that I've just talked about. As you can see, there have been some that have been very aggressive and other ones that have put this out there. So pretty much campuses, even though they may have a real green reputation, are doing some very innovative things. Not all of them are real aggressive with what they're going to do for their carbon neutrality goals. I think that Oberlin's is a very good goal. It's a little bit on the side of aggressive, but it's also, I think, possible to get there. So what do? We need an energy strategy certainly that will support what we say by what we do and leads by example and provides the best value. And it will not only be just changing the technology, it'll be also how we live and work on campus, so that we only use what energy we need and when it's needed. We certainly need to upgrade and make more efficient our systems and our buildings, but until we do that, it'll be largely dependent on our behaviors. So then we'll add renewables where we can, and then for the things that we can't, such as transportation technology, and I haven't heard of anybody yet saying that there's going to be a different type of engine for vehicles other than an internal combustion engine, we may have to buy some renewable energy credits to cover those. So again, use reduction, efficiency, central heating plant is a big piece of this, and then convert to renewables where we can. This is more of a visual of what I was just talking about. Certainly the cheapest energy, or the negawatts as some of them call them, cheapest energy that you save is the energy that you don't use. So again, behavior area, we're certainly trying to work with students through the resident portion and training of our student workers to try to talk about how we can live more sustainably and energy and resource reduction across campus. We're going to re-emphasize our recycling and reuse areas, and we also have begun a rubric to assess the greenness of student rooms and staff and faculty offices. The student room rating system is already online. Bridget Flynn has pulled that together, our sustainability fellow. Certainly take a look on our website to see how that's going. We have over 100 students already signed up for that. And we're developing one for staff and faculty. And these will basically be to help educate and do it by having the conversations in the office areas and in the residence halls where people can talk and be able to look and see what their neighbor's doing and people learn from each other. Because we want to hit the broadest group that we can of staff, faculty, and students to try to say, hey, we're all responsible for reducing what we use. Because technology alone isn't going to save it, because even the most energy efficient lamp uses the least energy when it's turned off, so behavior does matter. I know every presentation I have, I'm going to put that up, but I'm going to try to make sure to print it on the back of everybody's eyelids. So we are doing work on energy efficiency. We have a huge lighting retrofit initiative across campus. Last winter we did 1.2 million square feet. We're doing another 700,000 to 800,000 square feet. In fact, over winter break we went into, what was it, Bridget? 15 dorms, I think, and we replaced lamps in most of those. We're planning to pick up some of the rest of the academic and administrative buildings to do that. We've been putting in fact, in Firelands alone, we put in over 500 LED lamps in Firelands over fall break. So we're slowly converting to LEDs and high efficiency fluorescents. We have a kickoff meeting this coming Friday to put LED parking lights in 5 parking lots across campus. And at this point, we expect savings of 10 to 15% for lighting use. We need to take a look at our motors with variable frequency drives for fans and pumps to make sure that they're as efficiency as we can. And then our building envelope upgrades and our building heating and cooling system distribution upgrades are extremely important in our energy use, especially as we look to our heating energy, which at this point has been more for conventional fuels. So we need to do the work in our buildings to make sure that they use as little as possible. Central heating plant is a key component of this, certainly, because like the one that's there now, the next one and what we plan to do will be there for 50 years. So we've been doing a thorough evaluation of what we're looking at for centralized systems versus regionalized options. I'll talk about that in just a little bit. And we're taking a look at all the different types of things that we could do. There have been 4 studies done on this over the last, when was the first one done, Dave? Do you remember? PSI, I think, did the first one?
4 years ago, I think.
Okay, so 4 years. So in the last 5 years, we've had 4 studies. Professional Services, Inc. is what PSI stands for. They recommended 11 megawatt biomass-fired cogeneration plant. I don't know where they were going to be getting the biomass from. Maybe they were going to be hauling the pellets, I don't know. But the issues with that a little bit, besides biomass, is the fact that this would also allow the college to not only completely heat its plant, but also completely electrify its campus. Now the issue with that is because the college is 25% of the municipal utilities use. Certainly if the college were going to make all of its electricity, it would have a significant impact on electric rates for the rest of the community. If you take 25% of the bill out and you spread that over the other 75% of the residents, everybody in town's electric bill would go up. That doesn't make for very good town-gown relations. So though we could do something like that, it may not be the best way of doing it. EVI, which was Energy Ventures Incorporated, pretty much came up with a very similar type of operation, except at that time we were hoping that we might have an opportunity to retain some of the landfill gas from the local landfill, but that wasn't able to work. And then Black & Veatch, who came in to try to take a look at what they thought might be the most realistic in light of what was going on, recommended a natural gas-fired replacement plant. So, in taking a look at all of that, we had Stantec, who's been the latest group that's looked at this, use all the information from the PSI study, the EVI study, and Black and Veatch to come up with some ideas for a new plant. That, along with the staff and faculty on campus, we challenge them to think outside the box and say, what could we do? So we're thinking of, at this point, it would be pretty much look like a hybrid system. We would have a central steam plant that would run on natural gas during the development of self-sufficient energy zones, and CHP would eventually be fired mainly to supplement on the coldest days and to provide backup in the event that other systems didn't work. So the Stantec option is an Oberlin-specific hybrid based on development and utilization of the best available resources that we have, and we've just gone through many of those. The things that we looked at, as you can see, as part of Stantec studies: steam boilers, the landfill gas partnership, smaller distributed boilers across the campus, district geothermal, variable refrigerant flow in different buildings, which I believe they put in the second floor of Gibbons this last summer. And so we're checking that out to see how well that's going to work. There are plans to move it to the first and third floors as well. And then pulling this stuff together and developing a hybrid. Now, unfortunately, use hybrid car for an example, as opposed to an actual hybrid system, because I don't think we really have a picture of one. So when we take a look at our centralized system, I mean, this is the current heating plant. You take a look at the portion with the two big windows on the end and the large boiler and the rust stains that come down, which is the east side of the central heating plant. That is where the two coal-fired boilers are. The portion behind it with the square stack to the west is where the one natural gas boiler is that we have. Down below on the first floor, we have all of the chillers, which provide chilled water for air conditioning for the buildings that we air condition, as well as a backup generator for this area, and some air compressors, and also the cogeneration facility. Over on the right-hand picture there, the big pieces of equipment with piping going up are what are called electrostatic precipitators. They're the only type of control technology that is on the coal-fired plants right now, and it's to knock down the large particulates. The new EPA regulations are going to require even more extreme control technologies in this, probably with bag houses, to try to deal with the fine particulates, or the PM10, the mercury, as well as the nitrous oxides and sulfur dioxide. Again, here's what's served again by the central plant. But instead of looking at that, we can talk a little bit what's the difference between the two. The energy zones would be energy independent. We would try to work through building develop and distribution control upgrades to minimize the demand, and then remove that demand slowly from the central system and allow for a gradual move to electric energy. This is what a zone system might look like as compared to a centralized system where everything is served the same. Each of these zones here, and there's 7 of them identified, could be its own energy district where the bulk of the energy that they would consume could be generated from systems that are at their sites. The royal blue one is kind of the athletic complex up on the north end. You've got the red is where the Green Arts District would be. The green is where the conservatory is. The light blue is one of those that I talked about before, where maybe you could take the north residence area and heat all of those residence halls in the wintertime with a ground source geo-exchange system, and then maybe use the cooling load from the science complex to offset the heating load to recharge the well field in the wintertime, and then keep the heating load along with all of the rest of the buildings in orange, perhaps on a smaller centralized loop that could be fired with steam from either natural gas, or if there gets to be a local source of biomass or biogas or some other technology that hasn't been invented yet. And then you've got these other buildings to the south whereby you could perhaps run them, and maybe the buildings in the south could be both heated and cooled. Maybe we would have some more residence halls that we would put on air conditioning, thinking that we might have warmer summers coming into the next 10 to 20 years. And that might be an area where you could run, again, the bulk of that on geo-exchange ground source systems. So there are a lot of different ways to look at each zone. Each zone could be developed independently and phased over a period of time, so that you could phase the cost as well as the technology. It would allow us to where we may be able to adapt to new and upcoming technology in the future that maybe isn't even identified yet, as well as to fine tune and make sure what we can do in each one. And then as we're developing one zone, we can be working on the efficiency of the buildings in the next one. So if we were to start in an ideal world, the first thing we would do is to educate everybody so they use the least amount of energy possible. Then we'd upgrade all the buildings and the distribution system, heating distribution system, so all the buildings would use as little as possible of what was left over. Then we develop our energy zones to try to reduce the demand on the central system. And then we would only build the central system as a supplement or a backup to meet the demand, because we need to make sure that the backup is reliable and redundant, and then slowly convert it to more renewable systems. Unfortunately, we don't have an ideal world. The real world that we have is that these air emission regulations are going to be coming into effect in 2015, and we're going to need to adapt the central heating plant to that, because we aren't going to be able to do all the other work in the sequence that we would like. So the first thing that we could do here is to be able to address the current central heating plant. We need a secure and reliable source of heating to act as a baseline so that we have the ability to heat and cool all the plants while we do all the other work to slowly reduce the amount on the central plant. At this time, it appears that natural gas is the best resource to use as a bridge to do this. It's readily available and it can be turned on and off. We don't have to use it unless we need to use it. So the next steps would be to replace the coal-fired boilers with a natural gas system. That leaves us with a secure, reliable on-demand supply, and it will be a bridge as we move toward the hybrid systems. Then we continue to upgrade the building envelopes, as I talked about, and the heating distribution system, and fully develop the energy zones so that we can slowly reduce the demand on the central system and keep chipping away at the fossil fuel use. Currently right now, we're in schematic design. It's almost completed for the coal boiler replacement with natural gas boilers, and we have construction estimates in progress, as well as what we're going to do with the building if we took the coal boilers out of there, because at this point there would be an addition to the existing central heating plant so that we could build a brand new plant and then over a summer tap in and tie into the existing one. We're looking at adding 2 to 3 larger boilers, which would work with a retrofitted number 3 boiler, which is our current natural gas boiler, so that we would use the existing gas boiler along with some new ones to be able to run the central heating plant for the system. We're looking at design fees and construction estimates to present to the board in December, and also to identify specific building upgrades that we would like to do on campus, as well as develop one of the energy zones. The one that we're looking at is the Stevenson energy zone, because all the buildings in that zone are already there. We know what kind of demand they have, and we need to do some work in that area with the buildings anyway. We want to do these in parallel with the central heating plant work so that we get a jump on the conversion to electric compressor. And if we do that, where can we be? Well, here might be greenhouse gas inventory projected for 2015. If you take a look, we aren't purchasing any renewable energy credits on the bottom. Our metric tons of carbon have gone from 45,000 down to 17,000 metric tons, which is a 63% reduction from the 2007 baseline. And these aren't just on paper, these are real reductions that we can make. And a big piece of that is attributable to OMLPS did, or the city municipality did, by providing the 90% electricity for renewable sources. So if you add all those together and we get a credit for the new solar system that we just put online, and as well as the Lewis Center, you see the coal burn 0 tons. We will have an increase in natural gas burn, and I included a little bit of efficiency with that, but basically went 1-to-1 BTU to BTU to make the conversion come down in the end. So that is hugely significant. I can pretty much say there will be hardly any campus that has made real reductions to this level anywhere across the country, so we will be one of the first ones to do that. As you can see the difference, this is where we were in 2007. You had the 39,000 and the 8,000, you got 47,000 metric tons of carbon, and we're talking to take 30,000 tons of carbon out of our greenhouse gas inventory. So, where do we go from there? Because we still aren't carbon neutral with 17,000 metric tons of carbon. We need to keep going, and if we're going to try to meet our goal of 2025, there's only about 10 years left. So if we can assume that we can reduce the amount of natural gas or BTUs used by upgrading our buildings. We can make that 10% reduction, and then if we can take that amount and convert it to 75% from compressor heat due to the air-to-air and ground source heat pump systems, and then if we also get an 80% reduction in miscellaneous category and get local tree planting to offset 50% of our transportation footprint, which, by the way, I understand there were 25 or 30 trees or so planted in Tappan Square over this last weekend. So I know there are people hoping to continue to do that. We could get down in a range of 6,000 metric tons of carbon. If you took a look on some of our earlier renewable energy credits, we bought 7,000, 8,000, 9,000 metric tons worth of renewable energy credits, and it wasn't overly expensive. We could still utilize a little bit of funding to continue to buy the RECs to get that last bit, 6,000 tons down. So we've done it in the past, we could do it again. It's mainly, again, from a little bit of fossil fuel that we would need to use in the extremes, from transportation, as I talked about, and since only 90% of the electricity is from renewable sources, there still would be a little bit of residue left. Because our final goal is, he who burns the least amount of fossil fuel wins. That is our goal. We want to minimize this. If we can get to zero, we will, but I don't think we can do it without buying renewable energy credits. So that is our plan. That's what we've looked at, where we've been, and where we appear to be heading at this point. I guess I'd like to thank you for listening and to open the floor for questions, and both Professor Zohr and Professor Benzing will also be available as part of this to help answer questions. So again, thank you.